Hey everyone, like I said here, I'm Raunak Sarbajna, and I'm a PhD student here under Dr. Christoph Eich. I work at the DICE lab under Dr. Eich, Data Analytics and Information Systems lab. I've been here since just after COVID. I joined fall of 2020, and I'll probably be graduating this summer. And what I'll be talking about today is a little bit of my background and how I came into the research that I'm doing today, and a little bit about an overview of my research, my published papers, and what my background is and why I came to do the research that I came to do. So, my PhD research is essentially what's written here. It's spatial computing frameworks for adaptive disaster response and visual place recognition. And this is a lot of jargon. So I'll be talking about what all these three phrases are. What do I mean by spatial computing frameworks? What do I mean by adaptive disaster response? And what do I mean by visual place recognition? Okay, and oh my God. I hope I don't have to click several times just for the PowerPoint. Okay, so just as a background, I'm from India. I'm from Calcutta, India. And I did my undergrads over there. Then I did my master's at the Indian Institute of Remote Sensing, which is under the Indian Space Research Organization, who launches rockets for India. After that, I came to Lamar University, which is down in Beaumont, near the Louisiana border. And after that, I joined, under Dr. Eich, I joined University of Houston at the DICE lab, like I said, just after COVID. It's a vague summary of my background. You don't need to, I'm not going to quiz you on this, don't worry. So, these are the things that my research background prepared me for. Geospatial analysis and spatial reasoning. I did my master's back in India in these topics: remote sensing, geospatial analysis, GIS, SLAM, spatial computing, all of this stuff. I advanced my research also to include visual place recognition and SLAM. SLAM means simultaneous localization and mapping. I'll talk about what that is. And roughly around 2013, 2015, when AI networks, when neural networks became much more powerful than the existing geostatistical techniques, I switched to using those for my solutions. Before that, all of my research primarily used geostatistics and other older statistical techniques. I've also dealt with crowdsourcing. I've also dealt with agent-based modeling. I've published papers on both of these things, on crowdsourcing and agent-based modeling, but those are incidentals rather than the core focus of my research. So I have a bunch of publications. Most of my publications deal with my crowdsourcing work, my agent-based modeling work, which if you look at the bottom right here, this is currently under publication at the Society of Epidemiological Research in Boston. The conference is right now, it's going on, it started today, and I have a paper being presented over there right now, which is a city-based agent-based disease spread modeling framework based on COVID-19. I've done disease modeling work, then crowdsourcing work after natural disasters, disaster mapping systems, as well as human action recognition systems. My contribution to these number 2 and number 5 are mostly coding rather than the actual research itself, but it's part of my publication work. So let's go to geospatial computing and what my research is. And if you decide to join Dr. Eich's lab, the DICE lab, a lot of our research deals with geospatial computing. Not all of it, but a bunch of it deals with geospatial computing. Now, geospatial computing is, you all know what geography is, and you all know what statistics, maths, computer science, what all of these separate things mean separately. What geospatial domain means is analysis of all of these things together, right? So this means whether, say for example, you're doing oil drilling, or mining, or prospecting, or weather patterns, weather prediction. All of these require both your standard computer science stuff, but it also requires a lot of understanding of geography, right? So it requires understanding of computer vision stuff, of imagery, because a lot of these images that we work with come from satellites or from aeroplanes or from helicopters or drones. that are in the sky looking down orthographically. So all of these things require understanding of both computer vision stuff as well as geography stuff, and geospatial computing falls within that intersection. Now another major part of geospatial computing, other than the standard computing stuff, is localization, because maps, images, they don't float in the void, right? All geographical images, all satellite images, any geographical work requires you to tie that image, tie those statistics to an actual physical point on the ground. So, and that is what I mean by localization. So any image that you take from a satellite, whether it's like infrared images, radar images, SAR images, LiDAR images, they have to be localized, they have to be georeferenced, and that is that is its own domain. Because localization is not just here, localization is also needed by, for example, by drones, by robots, by self-driving cars, by all sorts of different fields. But in geospatial computing, localization specifically refers to georeferencing, where you take an image and find out what latitude and longitude and altitude it is in. So, and all these three things together are essentially part of my research. So I'll give you a couple of examples of what kind of, what this work looks like in practice when I'm doing it. These images are pretty old, because this is what I was doing back in Lamar and the early days of UH. So this is not representative of my current work. What I'm doing here is essentially creating what's called a REM, a river elevation map. So a river elevation map is essentially, you may have heard of dams, you may not have heard of the word dam, but whenever you open up Google Maps or Apple Maps and it shows you a 3D view of whatever you're looking at, that is what is called a digital elevation model, right? It's essentially, it has taken an entire model of the Earth, and on top of it, it has put the texture of the actual places on Earth. And this is kind of the similar thing, but this is done with rivers, so that we know that rivers essentially flow downhill, but that downhill movement, say for example, you're looking at the Mississippi River, that downhill movement might not be very obvious to you when you're looking at it with just your eyes. So for that purpose, we create things called river elevation models to understand these minor elevation changes in terrain more obvious. So these are examples of what my work used to look like 3 or 4 years ago. On the left, you see a standard digital elevation model, and on the right, you see that same area, but it has been the difference in elevation has been extended. So this yellow line is the river, and it is, you can see that changes in terrain from the right to the left. So you can see that the river is essentially flowing downhill from right to left. So that's an example of the kind of work REM does, and it can be quite beautiful, if I say so myself. This is the Snake River in Grand Teton National Park in Wyoming, and I created this. I made a blog post about this a while back as well, but you can see that you can make quite beautiful stuff just out of river elevation maps, and essentially coloring the different elevations differently. Another part of what I do is, I have no idea what that is. These are examples of what I do. So this is SLAM. SLAM means simultaneous localization and mapping. So what the term means, you can understand it from what the words are saying. It is, as you are moving about with a camera on a robot or on a self-driving car or just by yourself, it is simultaneously localizing. So it is immediately knowing where it is, and it is also mapping its surrounding neighborhood. You can do it using just images, there are certain machine learning models that do it for you, or you can use LiDAR, which is laser imaging detection and ranging. You can use, there are various forms of mapping an area, and this is a very famous example from a DARPA subterranean challenge, where you were given multiple robots and you were given an entire underground region, and you'd have to map out that entire underground region without knowing beforehand what it looked like. So this is what simultaneous localization and mapping in practice looks like. So all you have is a robot with cameras, and using that, and as you're moving, you're constantly mapping the world around you, and you're figuring out where you are based on that. This is used, for example, by a form of SLAM is also used by self-driving cars like Tesla or other self-driving cars that are currently available. So my research focus, and if you work with me, and this is what you'd be doing, I am using mostly state-of-the-art tech. Some of my tech is old, but most of it is state-of-the-art for real-time cartography, blockchains, but not blockchains as in crypto or blockchains as in Bitcoin or anything like that, but blockchains as in the purest form of blockchains, as a database, as an immutable database essentially, like I said, as an immutable database. That's what I use blockchains for, and visual place recognition to develop a crisis mapping system. And a lot of my work was inspired by and worked with the good folk at the Johnson Space Center at NASA. So a lot of my later work also focused on off-world settlements. So I worked with NASA images of the polar images and other NASA lunar images to create a mapping system for the moon as well. This research is currently in progress as well. So if you're working with me, you will be working with a lot of lunar images, which are a pain to work with. I can promise you of that. Lunar images are old. The visual place recognition part I'll explain slightly later, but what visual place recognition does is what I told you what SLAM does, but that in SLAM is doing what visual place recognition does in miniature. So VPR means, for example, if you using your phone, if you take a picture of the skyline of, like, say, downtown Houston, or a more recognizable skyline like New York or London or Shanghai or whatever, your camera tells you, okay, that skyline is, you're looking at a picture of New York, or you're looking at a picture of Shanghai, you're looking at a picture of Beijing, etc., etc. That is visual place recognition. That is, take a photo of a actual physical real world location and a model that tells you, okay, I think with like 90% probability you are in this location on Earth. That is what visual place recognition does, essentially. And that is what I'm also doing right now. But while VPR systems work very well within cities, they work poorly outside of cities. So that's what I'm trying to improve right now. So this should be a video. Should be an auto-playing video. So this is kind of a major problem with a lot of these modern machine learning models and modern machine learning solutions to problems. What happens is that as we try to generalize the models, like we started, LLMs were very different, vastly different from what they are today than they were like 10 years ago when we were just using BERT or whatever. Computer vision models, generative adversarial network models, they were highly specialized. They were highly focused on doing one particular thing. But as these machine learning models are getting faster and faster, people, what they are doing is they are trying to create a model that does, machine learning model that does everything, essentially. And so the scope of the model narrows. And what happens when the scope of all these different models narrows is that all these models start behaving similarly. Like all these different, whether it's what's famous right now, like all these DeepSeek, OpenLlama, Gemini, Palm, BERT. What happens is, as all of these models try to solve the same problem for everyone, these models start converging into becoming the exact same thing. So a lot of my research has been creating novel models that don't work in spaces that are already fulfilled by existing models. And if you're doing research, a lot of your work will be similar. You have to find niches where existing models don't work, or they don't work very well, or they may work well, but humans work better. So you have to find those niches and you have to target those niches. So that's kind of like a lot of modern computer vision or machine learning, AI-related research is dealing with these very narrow scopes. I'm not saying that you can't work on the entire hypothesis space on your own. You can still work on fairly large models, and you can work on much more general purpose tools. But for my PhD research or for any hyper-specific publishable research, you have to figure out representations like that target your solution. So whatever problem that you're trying to solve, whether it's in my field or whether it's in any other different field in this entire department, you have to find your niche, essentially. So let me talk about adaptive disaster response, right? Because this has been part of like my first 2 years of my research dealt with this, and I created 3 different models, published papers on them, and still publishing on them. So what do I mean by adaptive disaster response? So this is Hurricane Beryl from July, I think, last year. So a lot of disaster response research in Houston. I mean, Houston is pretty famous for doing like high-profile disaster response research, mostly because Houston has dealt with a lot of these kinds of disasters. More than like natural disasters, of all the major cities in the US, Houston deals with a larger quantity of this kind of natural disasters than almost any other major city in the US. So Houston has a very robust disaster response system. So and a part of that, and I hope I made these videos loop because they look much better with the loop, whatever. So my research essentially is how do we deal with the after effects of a disaster, right? So when the disaster is happening or pre-disaster, I can't really give any solution to that. So what my entire research work, like first years of my research worked on, is after this disaster has happened and roads are flooded, there's no power or whatever, and people are stuck. How do people contact with each other? How do people move about? So that's the kind of problem that I was trying to solve. And a major source of information just after a disaster, when Google Maps, Apple Maps, etc., these are not like up to date, they are not working correctly. And so the big source of information are the people themselves, right? Everyone has cell phones, even if they don't have connections to the internet, their local networks, their Bluetooth, etc., Wi-Fi would be working. So they are your big source of information just after the natural disaster. I'm not talking about like weeks or months after when the infrastructure has been rebuilt. So what I did was I created different modules, different solutions, that rely on just people with cell phones and nothing else to map out locations, to figure out like which roads are blocked, where are people able to go, how has the ground changed from what it was previously before the disaster has happened. And to do that, I created, like I said, I designed a system that assists in rebuilding the maps of the affected area immediately after the disaster, and I do it using crowdsourcing. And the crowdsourcing, the data is stored using blockchains. So this was a disaster scenario I tried to model in my paper, because you can create any system you want, but if to publish the paper on that system, to make people like to get people to use this system, you need to show them how it works in real life. So I used Hurricane Harvey as an example. I used maps like this where it shows like which roads were blocked during Hurricane Harvey, what was the extent of the water, and essentially how you do this kind of research, how you train this kind of model, is that you take a map like this and then you recreate it in your computer as a graph, right? As just nodes and edges of graphs. So all these road systems creates a massive graph of like thousands of edges, hundreds of thousands of nodes. And then what you do is, you know where the big population are, like where people live, and you put agents in them. And you give those agents rules on how to move about these graphs, right? You tell them that, okay, you place small agents on all of this, and you tell them, okay, if the water level is above a certain height, you cannot go through. You take demographic data, like what percentage of people in certain locations use cars, what percentage of people in certain locations use buses. In Houston, that was almost 100% everywhere. People use cars, so it wasn't very useful. But that's you set rules like this. Then if you're, where do people want to go? So if you're stuck in say third world and you want to go to the closest Walmart, you want to go to the closest HEPs, so that's where you would want to go. So every agent has desires and goals, and every agent has rules they have to follow, right? An agent can't just leave their house and spend the entire day going about to different HEPs and Walmart. They have certain limits they have to follow, and so using all of these like individual goals and targets and limits, you can create a system that kind of resembles real life. And what happens, in the end, what it does is you compare what the map that these agents have moving about have created, and you compare that with the real world map. And then you see, okay, my map is like 30% correct, so it's like almost 70% wrong. So what rules do I need to change? What do I need to update to make this work? And you iterate based on that. And that's what I did. I tweaked the blockchain that we are using. I tweaked the rules that we are using. I tweaked what kind of cell phones people have, how are people able to connect to each other, and I designed this system, iterated the system over and over and over again until I got to enough accuracy where I can say that, okay, this system can be deployed. And that's what I spent a couple of years on, and I published a couple of papers on this. Yeah, so like I said, we have to, these are the assumptions, because you have to assume some stuff before you're modeling something. And these are the assumptions that I made. The communication networks have been disrupted, area infrastructure has been disrupted, and I also assume that people have cell phones. If they don't, then none of this matters. Right. So these are the two models that I created, Deimos and PhobosBC. All the names of my models, Deimos, Phobos, Proteus, Nereid, these are moons. Deimos and Phobos are moons of Mars. Proteus and Nereid are moons of Neptune. So again, if you're creating models and you're trying to publish them, it's much easier. It's kind of an advertising tool if you give them good names. It helps people talk about them. It helps people call them easier. And then when others use it, it's easier for them to refer to it as well. Instead of if you just say, okay, I have designed a system to do this, and then you name that system. Just like as an advertising or just as a PR stuff. Okay. So crowdsourcing is a difficult thing to do. I mean, modern crowdsourcing is very different from crowdsourcing what it used to be 10 years earlier. But crowdsourcing in a post-disaster scenario had lots of challenges. So data source problems, data error problems. A lot of the data that was coming in was either unstable or inaccurate, because you can't really assume people are always going to give you correct data. So if people are trying to map out, they might try to make sure that their location is considered the most highly affected location, so they get aid faster. So these are minor things that you always have to deal with. So the system that we created was robust, was problem solving collaboratively, and it was highly decentralized, because we can't create a system that requires a centralized person to manage everything in a post-disaster scenario, because there isn't anyone to centralize it. This is kind of the very broad overview of the architecture. We had data collectors, we had data processors. These are just essentially two different types of software that were in people's cell phones, that were the data collectors were just moving about and collecting essentially information on where they were walking. The processors were taking that information, cleaning it up, and uploading it to the blockchain ledger. And from that ledger, anyone who wants that data could access it, whether they're on the ground or whether they're the government, first responders, whatever. So yeah, like I said, I'm going to skip over this data collectors and processors. This is again a very broad overview of what it looked like. Data collectors moving about, data processors taking their data, processing it, and uploading it to a blockchain ledger. And this is what our model looked like, because again, to test it out, we created an agent-based model system to work to see how it would look like, how it would work in the real world. We had a crowd movement simulation with different rules that I talked about, and data process. All of these were Python scripts, and I was using the Viper smart contract to connect to a blockchain ledger. a distributed blockchain ledger essentially spread across multiple different systems in the UH DICE lab. Next came Proteus, because one of the big challenges of this previous task is that people have to know where they are to tell you where to make sure to create the map, right? If people don't know where they are on the ground, then how are they going to create that map? And the second part is, once everyone gives you locations, like, okay, I'm at the corner of 5th and 3rd, I'm at this location, I'm at this location, like all these locations are coming in, and you have to figure out some way of, so you have two different challenges for this. First is figure out where they are exactly, and the second challenge is combine all of these into a map, essentially. So that like something that looks like Google Maps, something that looks like Apple Maps, so that you know, so that you're able to navigate using those things. So Proteus does the second part. What it does is it takes all these different data points from people, and it combines them to create a map of the ground, essentially. This paper is got published in a journal. It's a really big thing, so I'm not going to bore you with it. I can say people are already falling asleep. So this has like two different parts. One is managing the volunteers, managing the people, and the other is processing their data, which is trace processing. Again, this was evaluated using an agent-based model system with lots and lots of parameters, simulations, and our results. These are the two places where we checked it out. The University of Houston campus. So how closely were we able to recreate the University of Houston campus just by using crowdsourcing data? So what this means is that you give a bunch of people, do I mention how many? Okay, no, it's not mentioned here. But it's around between 60 to 100 people, cell phones, and you tell them to walk around the University of Houston campus. And using just that information, how accurately are you able to recreate all the paths within the University of Houston campus? And you can see that we were getting fairly okay-ish accuracy. It takes fairly long, but we were getting pretty good accuracy. And we also did it with downtown Houston, because downtown Houston, I don't know if you have seen it, it's very grid-like. It's all squares, and everything is like perfectly parallel, everything is like perfectly squared. So we were getting slightly higher accuracy. But the University of Houston paths are not that. They're like all curvy and weird. So we tested out both these different things, how closely we were able to come close to the ground truth map, how much longer it took, and what were the best methods for spreading out people within that location. And we did a lot of like statistical analysis. So you don't have to worry about what this is. What this is meant to show is that if you do this kind of analysis in your research, like if you have all this data, it's not enough just to have like this kind of data. You have to do like meta-analysis. You have to do hypothesis testing. You have to figure out like whether all the results that you're getting, do they mean anything, or is it just a quirk of randomness, right? So, and because people, when you're publishing this research, people are going to ask you that, right? People are going to ask you, like, what guarantee do I have that whatever model that you have created at 90%, 92% accuracy that you're getting, what guarantee do they have that this model is going to work on their location as well? What guarantee do they have that we haven't just created this data ourselves and just let people like giving like completely random results? So again, you have to do meta-analysis, you have to do hypothesis testing, and this is just one small ETA squared analysis just for testing out like different factors within the simulation and different hypotheses and different results. So these are, if you are doing research, you have to be really good at the statistics part of research as well, because without that, your results are going to be completely invalid. And there is especially in machine learning and especially in computer science machine learning, there's a massive problem called replication crisis. So this replication crisis, what it means is that people are taking papers that have been published over like the last 5 years or so, and those papers claim some accuracy, that their large language model is able to solve math problems at like 80% accuracy or 75% accuracy or whatever. And then what happens is that 2 years later, someone else who's trying to improve that model takes that old model, runs it, and sees the accuracy is like 30% or 40%. So this is called a replication problem. So without like solid amount of statistics, without making your code available, people just don't know that what you have created, what your research has done, is replicable or not, is reputable or not. Now there are some, there used to be some guarantees that okay, if your research is coming from MIT or Oxford or whatever, then you're almost guaranteed that this research is not bunk. But there's no guarantee of that, because nobody is going to go through all your data just to check whether you have done everything correctly or not. That you have to do it on your own. So that's why like you have to get really good at statistics, especially hypothesis testing, p-values, etc., etc. You have to be really good at that. And the final part of my research and the final part of my talk is Nereid, which is accurate geolocation. The Nereid architecture is for the lunar surface, but it works on anywhere on Earth as well that is outside of cities. So why did I start doing this? Because this came up slightly differently from my previous amounts of research. This essentially came from NASA themselves. So what they were talking about is, when I was talking about simultaneous localization and mapping and visual place recognition and all of that, they said that like orienting yourself and geolocating yourself on the moon is an unsolved problem. There are lots of different ways NASA is doing it. Essentially, they do dead reckoning. They have terrain relative navigation systems that do dead reckoning. What dead reckoning means is that an astronaut on the moon or a rover or whatever, they know where they have landed. They consider that as an origin point. They know that as 0, 0 on the XYZ axis. After that, every time they move, they update their location based on that. So if they have moved 1 meter north, then their current location is 1, 0, etc., etc. So that's dead reckoning. You know where you have landed, and then you are absolute as nicely as possible. You try to make sure you record how you are moving. But that is a hard thing to do, because if there is even the slightest amount of error at the start, it compounds on itself. So if you have an error of like a couple of inches, if you have moved like 5 miles, that error of a couple of inches might be like a quarter of a mile. So dead reckoning is not a final solution. So that's why I came up. I suggested to them this visual place recognition solution. And the other thing is, on the moon you don't have GPS satellites. It's why you don't have it is a big physics problem. Essentially, you can't have GPS satellites are always overhead, right? So they are geostationary. So from any point on the Earth, they are always overhead from wherever you are. But on the moon, you can't do that. If you try to create a lunar stationary satellite on the top of the moon, a satellite that orbits on the moon at the same speed as the moon is spinning, that satellite is going to get trapped on Earth's gravity well, and it's going to become a geostationary satellite. So you can't have GPS satellites on the moon. So and also the moon is gravitationally very lumpy. So any satellite that you have, all the current lunar satellites, they have to constantly correct themselves, because otherwise, within a decade, it's just going to, not even within a decade, within like a year and a half, it's just going to hit the surface of the moon. Because the gravity of the moon is not smooth and uniform. You have to constantly correct itself, and there's no atmosphere on the moon as well. So all of these things make that geolocation a fairly annoying challenge that NASA has been working on for decades now. Like I said, Dr. Alvenu, Ruth and Lewis, Dr. Howards, and Dr. McCabe, these are the people I worked with initially. I think some of you may have gone to the Johnson Space Center hackathons. This year it was in the Johnson Space Center. The years before that it was downtown at the Ion or whatever it's called. I forgot the name of the location. But yeah, if you're in Houston, and every year NASA has a Johnson Space Center hackathon, and I highly recommend joining it, because it's a very open, broad computer science hackathon, and you meet lots of scientists who are currently working in NASA right now. Sometimes astronauts come over as well, so you can talk to them. You can see what problems NASA are actually trying to solve, and you can if you can get internships. It's highly recommended. Always go to the Johnson Space Center Hackathon. So these are the research questions that I'm currently trying to solve. Whatever. Can you accurately geolocate on the moon? Is the tool that I'm creating, the landscape recognition tech, robust enough for 99% accuracy? NASA wants 6 nines. So NASA wants 99.9999% accuracy. But that comes later. First, I need to get to 99% accuracy. And the third question is, are our maps of the lunar surface good enough to create this kind of landscape recognition tech? Now, one of the side advantages of this is that if I'm able to create a tool that works with 99% accuracy on the lunar surface, it is also working with like much higher accuracy on Earth's surface, right? Because that's where I'm designing the tool. It's much easier to get images of surface of the Earth than surface of the moon. And again, these are side benefits of the research. So this is kind of what I've been working on over the last year or so. I'm combining different systems. INS, Inertial Navigation Systems, some of your cell phones have an inertial navigation system. It's essentially a gyroscope that tells you what the orientation, the attitude, the altitude of the device is. Visual place recognition, surface feature recognition, all of that to create a robust, reliable positioning system. So the way it works is that you take a picture, again, like I said, take a picture of anywhere. You stand on the surface of a street, take a picture, or you stand on the surface of the moon, take a picture, and the model is going to be able to tell you, okay, you have taken a picture of this location. The picture if you take multiple pictures, it's going to be able to tell you, okay, based on the pictures that you have taken, we can say with very high confidence you are in this exact location. And we are deploying the model, testing it, iterating it, and doing. So this is the kind of images that I'm training our model on. You can see rocks, boulders, hills. Another big challenge with lunar surfaces, if you work on this, is that there's no atmosphere on the moon, right? So if you look at the buildings very far away, you can see that the colors are fading of those buildings, right? You can see that because there's atmosphere, certain wavelengths of light get mitigated. So buildings that are far away don't look as clear or as colorful as buildings that are close by. But that's not true on the moon. There's no atmosphere, so you can't judge distances, especially humans. So everything, like the mountains, like you can't really tell whether this mountain is closer or this mountain is closer or this mountain is closer. They're going to look exactly the same. And also the moon is much smaller than the Earth, and so the curvature of the moon is much more obvious. So sometimes when you're taking pictures on it, when you're on the top of a cliff and you're taking pictures, you have to be very careful that the curvature of the moon is not tripping you up on how you're looking at it. So these are problems that during research you keep having to solve. So I'm using a bunch of different models to solve this. COCA, ResNet, VGG16. These don't mean anything to you, but these are the names of models that exist and that I'm modifying on my own and working. Yeah, so that's what I'm pretty much done, and these slides are essentially giving you information on what this kind of research looks like, visual place recognition. So you take a photo of a place, and then you take another photo of the place at night, or when it's covered in snow, or when it's covered in water. But a good, robust VPR model is going to always be able to tell, okay, this is the same place taken at different time location, different time periods, different weather conditions, etc., etc. Now, one big challenge is that all the existing VPR models, because these are existing VPR model images, these were designed to work on Earth, on cities, and now cities have you'll notice that cities have lots of straight lines and intersections. Natural locations on the whether it's on the moon or whether it's like in the jungle or whatever, natural locations don't have lots of straight lines. They have lots of curves. They have lots of odd shapes, and VPR models don't work very well on them. So again, that's what my research is, and that's what I'm trying to improve. And if you work with me, I have like lots of different niche problems in this location that you can solve with me. So that's pretty much it. And if you want to know more, contact me. If you're in 3337 Data Science 1, I'm one of your TAs, so you can contact me. I'll tell you what this research is. You can work with Dr. Risk, you can work with Dr. Reich, who is my advisor, and we work on this kind of information problems all the time. So, if you have any questions, now is the time to ask. Sure.
Yeah.
Well.
So, in regards to your learning modules with the Moon and Earth, you were explaining how Earth has not only an atmosphere but a wider curvature. So, how exactly would the learning models be able to work together? Because wouldn't that be like two completely different?
Yeah, that is a major challenge. So remember, one of the very early on, I showed you how, like, if your models are very wide, if your models are very generalized, then it becomes difficult to solve the problems that are very niche. So you have to tune your model so that it works on those, like whether it is able to recognize, first of all, what kind of atmosphere, what kind of parameters it's dealing with, and then you are able to also solve this kind of. So you need two different models essentially. That's what your solution is. You need a model for Earth, and you need a different model for the Moon, and a different model for Mars, and so on and so forth. Yeah, go ahead.
I've seen somewhere where you could have like network routers or other devices that can send rays around them, and then they would detect objects next to them.
Yeah, so that's how like LiDAR and radar and these systems work. They bounce off radar waves and they get information. So you might have heard of sonar that's used by submarines. LiDAR is a same version of that, but it works with lasers. And so you use that for a lot of SLAM solutions. You use some kind of LiDAR solution or SAR solution to solve this problem. But basic cameras are cheaper and they're easier and they require less power. So if you can create a model that solves this, that is able to create like a mapping of the location around you using just cameras, it is better. Now there are solutions. If you look up something called NERF, which is neural radiance fields, you'll see that people have done a lot of good work on just taking a bunch of different images and creating a 3D model out of it. So again, this is an active area of research. So if you have like some way of combining these things, so it's an area of research if you're interested in it.
Any other questions?
Sure.
So the reason for gravity not being uniform on the Moon, is that because of mass, or is there some other factor?
It's because of mass. The geological structure of the Moon is such that there are mass concentrations. They're called mass cons. So the lunar surface has lots of different mass cons spread out over the lunar surface. So what happens is when a satellite is orbiting, in some locations the gravity suddenly jumps. So its orbit changes. So orbital parameters change. And then if you don't have what most satellites that are currently around the Moon, they are constantly correcting their orbital parameters. So they have engines to correct it, and it has to maintain the orbit circularization. Because otherwise, the perfect circle of the lunar orbit, it doesn't maintain itself without us making sure that it's not going over a mass con and it's not losing height. It also happens on Earth, but on Earth there are gravity concentrations. For example, there's something called a gravity low under the Indian Ocean, just south of the Indian Peninsula. There's a high gravity anomaly in South America, which are locations that satellites avoid. You'll find that there's an entire location over Brazil, over southern Brazil and over northern Argentina, which are locations which satellites avoid because of this kind of like gravity anomalies.
Okay, thank you, Raunak.
Thanks everyone.